In this class, we will show you how to configure FortiGate to operate in transparent mode and discuss differences with NAT mode. We will teach you how to make a decision that is fundamental to your entire FortiGate configuration. Which operation mode should you choose? Most people are familiar with firewalls operating as NAT devices, which hide the IPs of your private network. But in transparent mode, FortiGate forwards packet as a non-NAT device that doesn't usually hide IPs. Due to this, configuring transparent mode is slightly different. It has unique benefits and drawbacks. So we'll explore both the features and special considerations of transparent mode. We'll discuss when it's appropriate to use NAT and when it isn't. We will also show you how to configure some features such as STP, VLANs, and VDOMs that are configured slightly different in transparent mode and how to avoid some common mistakes. What do we mean by transparent? Is it the same as hidden? Can the client detect the FortiGate? No, they aren't the same. Although detection is slightly more difficult, a transparent FortiGate isn't totally invisible. Here, transparent only means that at the IP layer, clients can see through your FortiGate. A transparent mode FortiGate forwards packets without changing IPs. When the client receives a packet from a server behind a FortiGate, the packet contains the server's real IP. FortiGate doesn't rewrite the IP header, so the server's address and listening socket isn't masked. Likewise, in the other direction, clients send packets directly to the server's real IP address. FortiGate is a layer 2 bridge or switch. How is that different? Traditional IPv4 firewalls and NAT mode FortiGates are routers, not just switches. FortiGate virtual IPs also apply NAT, which does change the destination IP and sometimes the port number to hide your network architecture from clients. Source NAT too can hide the opposite direction, client IPs from servers. Transparent mode by default doesn't do either. So large organizations benefit. They usually don't want to reconfigure thousands of devices to define a new internal versus external network. They also may have dedicated routers that are separate from FortiGate. By the way, NAT has a side effect: you can join your whole internal network behind one IP on the Internet. IPv4 addresses on the Internet are few. Often, to get more public IPs, you must buy them from your ISP. So NAT lowers costs. But if you're deploying FortiGate as an internal rather than edge firewall, the external IP is to other parts inside your own network. You don't have to pay your ISP for that. So NAT doesn't benefit internal firewalls as much. Cost benefit doesn't apply in pure IPv6 networks either, since it supports many more public IPs. So those are cases where you might consider transparent mode. Always carefully plan and choose the operation mode. If FortiGate has already been deployed, this will disrupt your network while you reconfigure. But for larger networks, broadcast storms are possible and can disrupt the entire network until you configure forwarding domains. We'll show more about forwarding domains soon. First, let's see the difference between NAT and transparent topologies. Here is an example showing NAT. FortiGate has 3 connected ports, each with separate IP subnets and routes. All interfaces on the FortiGate have an IP address and NAT translates between networks. Firewall policies allow traffic to flow between networks. FortiGate forwards packets according to either static routes, which are based on the destination IP address at layer 3 of the OSI model, or other IP-based routing rules such as policy routes and dynamic routes. Clients on each subnet send packets that are destined for a FortiGate virtual address, not the real address of the server, and FortiGate rewrites the destination IP and/or port number to the real one before forwarding the packet. Reply packets are rewritten to replace the real source with the virtual. Here's an example showing transparent mode. Firewall policies still scan, then allow or block traffic, but everything else is different. First, only 2 FortiGate ports are connected, a port pair. Second, notice the physical interfaces on FortiGate have no IPs, so FortiGates won't respond to ARP. There are only 2 exceptions. When changing to transparent mode, you can specify a port that will receive connections from your network administrators and send log messages, SNMP traps, alert email, HA signals, and so forth. That is, management connections. You can configure individual interfaces with an IP to also apply NAT or PAT. Note that this is rarely required. NAT with transparent mode is usually a misconfiguration. Either FortiGate isn't positioned correctly in your topology, or the appropriate operation mode wasn't chosen. By default, a transparent FortiGate won't do NAT. Unless an upstream router applies NAT, which you see here, clients will send packets destined directly for the server's IP. Lastly, notice there are no routes. This is because FortiGate is forwarding based on frames like a switch or bridge, layer 2 of the OSI model, not IP packets like a router. First, let's talk about the physical difference between the examples. Only 2 ports were connected in transparent mode, one to the internal network and another to the external. Policies forwarded traffic between those 2 ports only, never involving another port. Effectively, they were bound, acting like a filtered pipe. Why? Port pairing isn't required. Just like in NAT mode, you can use more than 2 interfaces and forward between any. But port pairs are the easiest topology to configure correctly. Otherwise, you must plan to prevent layer 2 problems such as broadcast storms and loops. You might need to configure more. We'll show some of these problems and solutions later. You could make more than 1 port pair as well. Here's an example where 2 port pairs are used. This FortiGate has 4 ports, each connected to different physical locations, but traffic is not allowed to flow between all 4 locations. Policies only allow traffic between ports in the same pair, between port 1 and port 2, and between port 3 and WAN 1. So in this example, the network on port 3 can reach the internet through WAN 1, but the networks on port 2 and port 1 can't reach the internet. They can only reach each other. Next, let's talk about the second difference between NAT and transparent examples, the IP addresses. By default, transparent interfaces have no IP address. Instead, FortiGate forwards if the frame is destined for a MAC address that the FortiGate knows. With a port pair, frame forwarding is simple, from one link peer over a FortiGate bridge to the other link peer. But what if you don't have simple port pairs? What if you have branching? What if you have redundant links, creating layer 2 loops? Or what if there are other layer 2 switches on your network? There could be more than one path to the same MAC. Design of layer 2 of your network becomes crucial when you have multiple segments connected. To ensure correct frame delivery, different devices must not have the same MAC address. If there are multiple paths to one MAC address, you must configure your network to temporarily disable forwarding along most paths so that, for example, FortiGate doesn't deliver multiple ARP requests to the same device. Finally, for best performance, you'll want to always use the shortest viable path. You can configure this manually, but in complex networks, it's easier and faster to manage links and MAC-based forwarding via a Layer 2 protocol such as STP. Spanning Tree Protocol automatically ensures that there are no Layer 2 loops. By default, FortiGate does not participate in STP learning, nor forward BPDUs, but you can enable it. You must still restrict broadcast domains so that they are not overwhelmingly large, though. We'll talk about that next. With port pairs, you could only forward BPDUs, but with branching, you should configure FortiGate to participate. To enable STP globally, use the config system STP command in the CLI. To configure STP on each interface, use the set STP forward command while inside config system interface. Note that this is only supported on models with switch interfaces such as FortiGate 30D, 60C, 60D, 80C, and 90D. So now we've solved Layer 2 loops. What about broadcast storms and MAC flapping? At the beginning, we said to choose your operation mode carefully before configuring forwarding domains. This is very important with VLANs and VDOMs, features often used in large networks. In transparent mode, by default, each VDOM has a separate forwarding domain. Interfaces, though, don't. How does this affect branching topologies? Until you change the initial VDOM configuration, all interfaces connected through firewall policies are part of the same broadcast domain. FortiGate will broadcast from every interface in the VDOM in order to find the destination MAC address. On large networks, this could generate massive broadcast traffic and overwhelming replies, a broadcast storm. And as mentioned, you can't reconfigure the scope of the forwarding domain while it is referenced by address objects, firewall policies, or other parts of the configuration. So it's crucial that you configure it correctly before you deploy. Here's an illustration of the problem. A broadcast with an unrestricted forwarding domain. An ARP WHOIS is sent by a single device. It reaches FortiGate through one of the interfaces in the VDOM. Because they all belong to the same forwarding domain, FortiGate then rebroadcasts to all interfaces. This generates a lot of traffic, but in theory, the ARP reply still will arrive on only one interface, and FortiGate will learn that the MAC is on that interface. However, what if there is more than one path? FortiGate would rapidly switch between links because the last interface that receives an ARP reply with the MAC address will vary slightly. This will cause transmission problems. The three-way TCP handshake involves 3 packets, and if the IP session is transferred from one interface to another in the middle of transmission, the handshake will fail. Another way to restrict the scope of broadcast forwarding is to configure VLANs. FortiGate can be an IEEE 802.1q VLAN trunk in transparent mode. Here are VLANs with a transparent FortiGate. Traffic originates here on a computer and is sent to switch A. The switch tags it with VLAN 100 and sends it to switch B. In between switch A and switch B, you have a transparent FortiGate. it has interfaces with VLAN 100 and firewall policies to allow the traffic. This network was set up prior to deploying a FortiGate. So FortiGate has been deployed transparently to avoid the need for changes to the network. Once traffic reaches switch B, it removes the VLAN tag and delivers it to the destination computer. Forwarding domains are like broadcast domains, but for VLANs. When a VLAN frame arrives, Ethernet headers are stripped. The packet is inspected. Upon egress, headers are added again. Because forwarding depends on OSI Layer 2, not Layer 3, unless you properly separate your networks, FortiGate could accidentally send frames in the wrong direction. Here, the same network that we showed before for VDOMs, but here, VLAN 101 is only on two interfaces. Placing them in the same forwarding domain ID segregates them. Traffic arriving on one interface is only broadcast to interfaces that are in the same forwarding domain. If FortiGate knows the destination is on a separate network, a packet can cross to different forwarding or broadcast domains if a firewall policy allows it. Now it's time for the labs. In this lab, you'll create a VDOM that is configured for transparent mode. You'll also create an inner VDOM link between the transparent mode VDOM and a NAT mode VDOM.